Now, one of the important rules of square roots and real numbers is that you can't take the square root of a negative number. So we're going to start by assuming that every square root we're taking today is of positive numbers, okay, or 0. Just to make it easier, we're going to just assume that we're not taking the square root of a negative number whenever we have a variable under there. Okay, so if we see something like square root of x, we're just going to assume that x is greater than or equal to 0. Okay? Because if it was negative, then the whole question would be useless, and then you wouldn't have any homework to do, and the world would fall apart. Since we don't want that to happen, we're going to just avoid that altogether. Now, the first and most important property of radicals we need to know for today, and for the rest of the chapter, is the product property of radicals, which states that if you have a product underneath a radical, you can split it into the square root of each of the individual factors. And it's important to note that that property works both ways. Since there's an equal sign, you can go in both directions. So if you have two radicals being multiplied together, you can combine them. So for instance, the square root of 6 times 2 could be separated into the square root of 6 times the square root of 2. And the square root of 3 times the square root of 5 could be combined into the square root of 15. Because we can just multiply the numbers under the radicals. Make sense? So we're going to use this property, among others that we'll learn, to write radicals in simplest form. And there's a few rules that determine whether or not a radical is in simplest form. The first one is no perfect square factors under the radical, except for one. If there's a perfect square that goes into the number under the radical, then we have a way of simplifying that, and we'll work on that today. No perfect square factors in the radicand. Remember, the radicand is the number underneath the radical. So rule number 1. Rule number 2. No fractions underneath the radical. And rule number 3. No radicals in the denominator of a fraction. So, if those problems should arise, we have a pretty simple way to fix them. We have a couple of rules that are going to help us out with that. The first one is the property that I just showed you. The second one is another property we'll get to after we do a few examples. So in example 1, we're given the square root of 32, and we need to simplify it. So the first question is, what perfect square factor goes into 32? 16. How many times? So it's fair to say that 32 is 16 times 2, right? So what we can do is we can split that 32 into 2 pieces, 16 times 2. Then we can use that product property that we learned to split that radical into 2 separate radicals. Square root of 16 times square root of 2. And what's the square root of 16? 4. So that equals 4 radical 2. Make sense? Okay. Now let's put one up there with a variable in it. First of all, we can split this into the square root of 9 times the square root of x cubed. That's easy enough to see, right? What's harder to see is that there's a perfect square inside of the x cubed. Any ideas what it might be? X squared. How many times does x squared go into x cubed?
3 times. No.
X cubed is x squared times what? X. X squared goes into x cubed x times. Okay, because x times x squared is x cubed. Okay? So what we can do is we can split this radical into 3 pieces. Square root of 9 times square root of x squared times square root of x. Make sense? What's the square root of 9?
3.
What's the square root of x squared?
X.
And then we can't take the square root of that last x, so we just leave it underneath the radical. Make sense? Now, this is all well and good if you can easily identify what perfect square goes into a number. If you can't identify what perfect square goes into a number, it might be helpful to just write the prime factorization. Now, there's a couple of different methods for writing the prime factorization. I like to use the shelf method. Some people like to use the tree method. It doesn't really matter. Let's try the tree method because a lot of people like that one. What prime number goes into 275? Or what number? Just find a number that goes into 275. Yeah.
55.
55?
Yeah.
Okay, so 55 times 5 gives you 275. Okay, what can we break 55 into?
11 and 5.
11 and 5. And those are all primes, right? So what we could do is if I needed to find or simplify the square root of 275, I could split it into the square root of 11, square root of 5, square root of 5, right? What's the square root of 5 times the square root of 5?
The square root of 5.
Square root of 5.
What's the square root of 25?
5.
5. Okay. Square root of 5 times the square root of 5 is the square root of 25, but the square root of 25 is
5.
5. Whenever you're multiplying a radical by its twin, you just get the number out. Okay, I like to call it the buddy system. You guys ever use the buddy system for swimming, like at summer camp or whatever? And why do we use buddy systems?
We don't drown.
So nobody drowns. So here's what we see here with these numbers. 5s, they had a buddy. They didn't drown. Yay, they came out of the water. The 11, however, did not have a buddy. It drowned in a most radical way. Okay? Makes sense? So sometimes you get really complex numbers that you can pull out multiple numbers. Okay, you can pull out, the perfect square of 25, and then maybe a 16, and maybe some other numbers. And all of that stuff, just every time you get a buddy, it comes out. All right? So, example 2 gives you radical 6 times radical 6. Now, they take you through a couple of different steps, but we know radical 6 times radical 6 is
Regular 6.
regular 6.
Sorry.
That sounds more like a, clothing size. It's a regular 6.
Oh my gosh.
Okay. Now, the reason is radical 6 is a number so that when I multiply it by itself, I get 6. And here I am multiplying it by itself, so I should get 6. Right? Let's look at the next one. Radical 3x times 4 radical x. What do I do with that 4? Yeah, I can bring it out in front. It's not under a radical, so it shouldn't be moved under a radical. Right? But then underneath the radical, what do we get underneath the radical?
Radical
3x squared. Because I've got the x times the x gives me 3x squared. then I can split that, right? 4 radical 3 radical x squared, and what's the square root of x squared? X. So we've got 4x radical 3. Now notice that I put the radical 3 at the very end, even though there's an x in the middle. Why do you think I'd put the radical 3 at the end?
Because it can be simplified. Well,
Nope.
does it have to do with the one with like the most very
Nope.
if it has an x with it, it goes first in order. Like if it's x squared, then it goes x, then it goes.
That's for when we're adding with polynomials. We put them in descending order of degree. This has more to do with just avoiding confusion, because if I write this, you might think that the 4 is underneath the radical or the x is underneath the radical, and so this just saves you a little bit of confusion by saying, okay, only the 3 is under the radical. It's fairly obvious when it's written like that. Okay? All right, how about radical 7xy squared times 3 radical x? That's way over to the wrong side of the page. Let's move that over. First of all, that 3 is not under the radical, right? So let's keep it out. What's under the radical when we combine those two?
7x squared, no, x cubed, y squared.
I'm pretty sure it's still x squared.
X
X squared, y cubed. Oh, x
Y squared.
squared.
Just y squared. There's only the y squared. There's no y to make it a cubed. Right? Now if we split that up, it should be pretty obvious what's going to come out. What's our final solution? Biscuit.
3xy radical 7.
3xy radical 7.
Thank you.
Okay. Make sense?
Mm-hmm.
All right, now let's deal with the fractions. So we have the product rule, now we have the quotient property.
Oh,
Well, of course they're different. They have different names. Square root of a over b is equal to the square root of a over the square root of b. Quotient property. This will help us take care of the second rule, which says no fractions underneath the radical. The third rule, no radicals in the denominator, we'll take care of in the next lesson when we learn how to rationalize the denominator. So if you have a fraction underneath the radical, then you just take the square root of the top over the square root of the bottom. So let's start with a real basic example. Radical 13 over 100. What would that become?
radical 13 over radical 100.
Okay. Then what happens?
100 gets simplified down to 10.
That's right, the square root of 100 is 10. Make sense?
Yeah.
How about radical 7 over x squared? What does that become? Liz?
The square root of 7 over x.
Over x, right, because we'd have the square root of 7 over the square root of x squared, and the square root of x squared is x. Everybody get those steps? Any questions? That's it.